So as I mentioned earlier, we're going to start with a discussion of Berkeley packet filters. Now, the great thing about BPFs are they're really the standard language for filtering packets across the industry, so across both IT and security, and that's really demonstrated by all the different tools that support BPFs. It's a very well-defined, well-structured language. There are a lot of libraries that use it, so it's very easy to integrate into existing tools, which is why it's used by things like Wireshark and TCP dump that we'll cover in this course. But it's also used in things like Snort, the world's most popular network IDS, Suricata, which is another network IDS that's incredibly popular, NetSniffNG, which is a tool that basically just captures packets proactively. A lot of people use those for network sensors, and Bro, which is another network data collection tool most often used in security. So BPFs are used in pretty much everything. If you understand how to write Berkeley packet filters, you can generally interact with most packet capture utilities and do some type of filtering with them. Some operating system distributions even rely on those heavily. For instance, the popular Security Onion distribution that's used for network security monitoring, it uses several of the tools listed here. It uses NetSniffNG, Snort, Suricata, Bro, TCP dump, and so on, and it allows you to put a BPF into a single location and apply that to all those processes at once. So very flexible in that way and very robust. That's why I recommend everyone doing packet analysis or network security analysis learn BPFs first, and that's why we're going to start there first as well. That it's also just, again, a nice constrained language that's pretty simple, very flexible, easy to use. So that's why we're going to start there. Now, that said, BPFs are not quite as robust as Wireshark display filters. These are not based upon protocol dissectors, so they're not getting that specific. But nonetheless, still very simple, still very flexible, so that's where we're going to start. So let's go ahead and dive into learning some BPFs. The great thing about BPFs is they take a very predictable structure for the most part, and you can kind of see that with the BPF I have on the screen here. So this whole thing is called an expression, and without a lot of explanation, you can probably figure out what we're looking for here. We're saying match any packets where the destination host is 192.168.0.10 and the TCP port is 80. So we're combining two statements, so to speak, there into this one global expression. Now, of course, I have these broken out into more proper BPF terminology. I'll say that not many people actually use this terminology in practice. They call this whole statement a filter or maybe an expression and don't necessarily refer to its component parts as the spec says. But nonetheless, I do want to teach you the proper way here, so that way if you need to ask for help and you need to refer to these things individually or specifically, it allows you to do so. Now, with BPFs, there are really just 4 rules to remember. So I want to go through those here, and I'm going to leave this one on the screen so you can kind of understand that a little bit better. First, a filter is called an expression. So a lot of people are just going to call this whole statement here, a BPF, just a filter, and that's okay, but the proper term here is expression. So when we refer to this whole thing, we're just calling it an expression. Next, each expression contains one or more primitives. And a primitive is a group of qualifiers and IDs, or you can think of this almost as kind of like fields and values. So you see, in this case, we have 2 primitives that are joined by an operator. The first primitive is dest host 192.168.0.10, and the other primitive is TCP port 80. Now, each of these things on their own are a primitive, and they can also represent a whole expression when used independently. But since they're combined together, altogether, this represents a single expression. Now, as you can see, primitives themselves consist of one or more qualifiers followed by a value or an ID. A qualifier are things like dest and host, or TCP and port in this case, which is kind of what narrows you in to the specific fields you're looking at here, and we'll show some examples of other qualifiers later. But those are your qualifiers, and your ID in this case is your value. So in this case, our IDs are 192.168.0.10 and 80. Those are the values in the fields we're looking for. And finally, primitives are concatenated together or joined together with operators. So in this case, our first primitive is joined to another primitive with the AND operator. So both conditions have to be true in order to match a specific packet. We could just as easily join those with the OR operator that says one or the other has to be true, but this is the AND operator, and it's what allows us to concatenate these things together. With the same four rules on the screen, I do want to show you these two tables that show some of the qualifiers and operators that are going to most commonly be used. Now, starting with the table on the top right, we're looking at different types of qualifiers. So these are different groups of qualifiers. And you see we have three main types, and they are actually called type, dir, and proto. So that's the type, which identifies what the ID, name, or number refers to. So in this case, we're talking about host, network, or port. All those are pretty self-explanatory, right? Host is a single system, net is an entire network, and port is a specific port. After that, we have dir, which is specifically talking about the direction of a transfer. So we're talking about source or destination in this case. And you see we have those two examples, SRC and DST. And then finally, we have protocol, which restricts the match to a specific protocol, such as IP, TCP, or UDP. Now, in BPFs, you're generally concerned with network and transport layer protocols. BPFs are not really application layer protocol aware. So if you want to filter upon application protocols more specifically, generally going to do that with a Wireshark, like a display filter after the fact. That's one of the limitations we'll see of BPF filters is they don't have a lot of ability to parse those application layer 7 protocols. They're more lower layer filtering here. But nonetheless, we have these three groupings of qualifiers: type, direction, and protocol, and we can combine those in various ways. Certainly in the example we just looked about, we saw where we combined dest and host, and that means destination host, right? So we have the ability to combine those. We'll see that as we continue through other examples. Of course, we also have this notion of concatenation, right? We're concatenating with operators, and we see those down at the bottom here. So we see the AND operator, which is 2 ampersands, the OR operator, which are 2 pipes, and the NOT or negation operator, which is an exclamation point. So we have the ability to do those things as well with the various operators. And again, these things will make a little bit more sense as we go through a few more of the examples. I mentioned a bunch of examples, so let's actually go through those so you can kind of see BPFs at work. So what I'll do here is I'll actually ask the question. I'll tell you what I want to filter based upon, and then if you want to, you can actually just pause the video right there, get your trigger finger on the pause button, and then you can pause it for a few seconds, think about what it would look like yourself, and then I'll show it on the screen so you can kind of check your work. So let's go ahead and do that. For the first one, we'll start with a really simple one. I have a host 192.168.0.1, and I want to match all traffic to or from that device. What would that filter look like? Well, pretty straightforward, right? It's a simple host qualifier followed by the IP address, host 192.168.0.1. Pretty straightforward. Now, let's say I want to take that same filter, but instead of getting traffic in both directions to or from it, I'll only want traffic that was created by that device. I only want to see traffic outbound from that device. What would that one look like? Another pretty straightforward one. We're going to take the existing filter and add another qualifier to it, in this case the source directional qualifier, and that's going to give us source host 192.168.0.1. It's going to show us all the traffic sourced from that host in one specific direction. Next up, let's say I want to match all traffic or all packets that are to or from port 80. What would that look like? Another simple one, port 80 is just that. We use the qualifier port, and then we specify the value of 80. So simply port 80. Next, let's say I only want to see traffic destined to web servers, so traffic going to port 80 in this case. What would that look like? You guessed it, just like the previous example, we're just going to add an additional qualifier based upon the direction, and that's going to be DST or dest port 80. Okay, now let's get a little bit fancier. I want you to take the same IP address we've been using, 192.168.0.1, and I want you to show me all traffic related to that host, both directions, but then I want you to limit that down to only traffic sourced from port 80. Right, so only traffic that's from port 80 for host 192.168.0.1. What would that filter look like? This one gets a little bit fancier in that we actually have two primitives we're using, and we're going to combine those into a single expression. To do that, we're going to say host 192.168.0.1, and so we're concatenating with 2 ampersands and source port 80. So that will give us all traffic sourced from port 80 to or from 192.168.0.1. Pretty cool. Let's build off that one and tweak just a little bit. I want you to take, again, 192.168.0.1 and show me that as well as TCP traffic sourced from port 53. What would that look like? Again, not too different from the last one you did, right? So we're specifying host 192.168.0.1, and we're concatenating again, so and TCP source port 53. In that case, when I gave the prompt, you might have noticed I pretty much gave you the filter when I said TCP source port 53. And that's kind of, to some degree, like a visceral reaction to describing how to write a filter. What you'll notice as you start writing more filters is you'll actually start talking about network traffic as you would write the filter. So if I want to tell someone I'm interested in TCP source port 53, I'm generally saying it just like that. Hey, what's the TCP source port 53 traffic look like? Is there anything there? Well, I'm doing that because I've written so many filters for so long that I almost talk in filter speak. And most people who do this, who look at packets for a living or do network security for a living, are going to do the same thing, and you'll find yourself doing that as well. As a matter of fact, for most of these examples, I had to specifically write down what I was going to say for the prompt rather than just give it to you from the top of my head, or else I would basically just read the filter out to you. So you'll get to the point where you're basically talking in filter speak, which is pretty cool. So one last one we'll do. Let's just say I want to see all traffic that matches 192.168.0.1 to or from, or all traffic that matches 192.168.0.2 to or from that as well. So I'm concerned about either of those two hosts, traffic that matches either one of them. What would that filter look like? The filter here looks similar to the last one. In this case, we have two primitives, one for host 192.168.0.1 and one for host 192.168.0.2, and we're concatenating them with two pipes, which means or. So what we're saying is if a packet matches one of those hosts or the other host, not both, but just one or the other, then it will match, right? So we're using that or operator to connect those instead of and. So these again are just a bunch of different example expressions. The truth is, if you can master the ability to create BPFs similar to everything on the screen here, and if you can work out these types of things on your own, then you're pretty much 90% of the way there with BPFs. Most things you're going to do are going to fall into these groupings as far as filtering based upon protocols, hosts, and ports. That's 90% or more of the things that you're doing. There's an extra 10%, which we're going to talk about here in just a second, which gets a fair bit more complex. But for the most part, if you can master creating expressions like these, then you're going to be all set. So we're going to provide you a few more opportunities to practice this as well. But focus in on this specific syntax of BPF expressions, and you're going to be well on your way. As I mentioned, the things we just looked at and all those example expressions will really get you 90% of the way there if you can filter based upon IP addresses and ports and protocols. However, what happens with that last 10% or so? How do you filter upon things that are within a packet but are not necessarily constrained to, protocols, addresses, or things like that? How do you do that? Well, we do that with a couple different techniques. The first of which is called byte level filtering. And byte level filtering basically allows you to filter based upon specific bytes within a packet and their value. So let me show you an example of what this looks like. We have here an IPv4 header. We haven't talked about IPv4 too specifically yet, but we have talked about packet maps and reading packets in hex. And this is where the rubber kind of meets the road on that and where some of the value lies in being able to understand what you're looking at and read these packet maps. So let's say, for example, we want to filter on something here that doesn't conform to any of the existing expressions we looked at. Let's say we want to look at the IP protocol field, and we want to look for any IP packet that is not GRE. So it's not a tunneling protocol. In this case, we're looking for things that are maybe not tunneled through the GRE protocol. So you don't have to know a lot about GRE. Basically, what you just need to know is that GRE in this case would be represented in the IP protocol field with the value decimal value 47. So we want to look for the protocol field and match anything that is not 47. So to do that, what we have to do is pretty straightforward, but you have to kind of get used to doing it. We have to find the protocol field and what byte it is in specifically. Now, if you're familiar with IPv4, you may know it right off the top, but if not, you may have to count it out. And remember, we count bytes starting at 0. So if you count the first byte starting at 0 and move along to get to the protocol field, you're going to find that protocol exists at byte 9, or at the 9th byte offset from 0. And you see I'm moving my mouse around that right there. So we're talking about the 9th byte offset from 0. Now, what that means is we have to specify that 9th byte offset from 0 in our filter and say that's where we want to look. And once we do that, we can actually apply an operator and a value to it. So in this case, our filter would look like this. And what we're doing here basically is what I just said, but kind of written out in a very specific syntax. So first of all, I've specified that we're going to look at the IP protocol. So I've just put IP, and then I've opened up a square bracket. And in those square brackets, I put the byte that I want to start looking at. And I say the byte that I want to start looking in because we can look across multiple bytes. I'll show you how to do that here in just a minute. But we're going to look at the 9th byte offset from 0 in the IP header. And what we're saying here is we want to look, once we found that byte value, we want to match anything where the value does not equal 47. So we're using the exclamation point equals to say does not equal, and 47. So IP9 not equal to 47 will help us find any IP packet where the protocol field value is not GRE, and that's pretty cool. That's pretty neat and fairly straightforward, right? So let's look at one more example of that here. Let's say we want to look again at the IP header, so the same header we have here, and we're looking for TTL values less than 64. So to do this, we have to find the TTL field. And if you found the protocol field, the TTL field is not far from it. It's actually byte 8. It's right before the protocol field. So to look at that, we're going to look at IP8, and we're going to say we just want to look at anything less than 64 bytes. So here we go. IP8 less than 64. Not too hard, is it, right? That's not too crazy. So byte level filtering is just that. It's the ability to find a specific byte within a protocol header and apply some sort of operator to it and look for a certain type of value. So we can match something straight up. We can say that a value equals something, or we can use greater than or less than or not equal to here as well. So these are a few additional operators in addition to the concatenation operators we talked about earlier. So pretty cool. Let's keep moving forward and dig into some more examples of that. For the next example, we're going to do more byte level filtering, but instead of focusing on the IP protocol header, we're going to focus on the ICMP header. Now, you'll see in this case, the ICMP header is much simpler, at least in this representation, as the ICMP protocol header really depends upon what type encode values you have, and it's going to be highly variable based upon that. But nonetheless, we're going to focus in on what we have here, and the first thing we want to find are ICMP type 3 packets. Now to do this, remember, we first have to specify the byte we want to use in the specific protocol. In this case, the type field is the very first field in the ICMP header. Now, we don't say that's ICMP1 because remember, we count starting from 0, and that's reflected here on this in this screen. So we start counting from 0, which means we are looking at ICMP0 as the specific byte we want to filter on, and then we're just going to match anything where ICMP0 equals 3. And we're left with this filter. So we have the ICMP protocol specified, 0 in the square brackets to indicate the 0 byte offset from 0, and then equals 3 to say we're going to match ICMP type 3 packets. Now let's extend that just a little bit further and say we want to match ICMP type 3 code 0 packets. So clearly you see we're going to start with what we already had. We're just going to build off what we had with ICMP 0 equals 3. Now the code field, you'll see that occurs right after the type field. So we're looking at byte 1 in this case. It's the second byte, but since we start counting from 0, it's byte 1. So we'll say ICMP1 equals 0 because we want to match code 0, and then we'll just simply concatenate those together with 2 ampersands to indicate and. So this will match any packet that is both type 3 code 0 within the ICMP protocol. Now I want to present you with a slightly different scenario based upon byte filtering. here we have the TCP protocol, transmission control protocol, which we've discussed a little bit, and we know it's a transport layer protocol that's used instead of UDP. You might use TCP. Now, what if we want to look at packets where the destination port, TCP destination port, is 443? Well, we'd go through our same process, and we could obviously just specify port 443 as in some of the other examples. But let's say we want to do that using byte level filtering. We could look for the destination port field, and we see here that it starts in the second byte offset from 0. But in this case, notice that it's not a 1-byte field, right? It's too big of a number to fit in a single byte. It's actually a 2-byte field. It spans bytes 2 and 3 in the first line here of the TCP protocol header. So how would we match that? How could we specify that? Because we can't just specify TCP2 equals 443, because at that point we're only going to be looking at the second byte. We need to look at both the second and third byte. Well, that's actually pretty simple and pretty straightforward. We're going to do that by adding just a little bit to the syntax here. And instead of just putting TCP2 with 2 in square brackets, we're going to put 2:2. And what this syntax is telling us is it's saying to the filter, hey, start looking at the second byte offset from 0, and then look for the width of 2 bytes. So look at a total of 2 bytes starting at the second byte. Right, so that's pretty cool. So it allows us to do that and then say, the value of that equals 443. Of course, we can also specify that in hex if we want. So we can say, start looking at TCP 2:2 and then show me the value OX01BB. In this case, we're specifying that we're looking for a hex value by using OX to indicate that what follows is hex, and then O1BB is the hex representation of the value 443. So pretty cool. We're actually spanning multiple bytes here using byte level filtering. Let's try another example where we're filtering by multiple byte fields. In this case, we're going to switch over to the IPv6 protocol, and we've not done a ton with IPv6 yet. It's a fair bit different than IPv4, but a lot of the same things are present. Now, in this case, we want to filter based upon a payload length larger than 124 bytes. So you can look down below and see that the payload length field starts at byte 4. So it's the second line there, which is the fourth byte offset from 0, and it spans 2 bytes. So to do that field, as you might expect, we're going to specify the protocol, which in this case is IP6, and then in square brackets, we're going to say start at byte 4 and look through 2 bytes wide of data. So 4:2, and then where we want to look at anything larger than 124 bytes. So very simply, we'll just say IP6 4:2 greater than 124. And that'll get us the result we're looking for. So pretty straightforward, the ability to filter based upon values in bytes that are spanning more than 1 byte, so multiple byte fields. Let's talk about one more example here that might trip you up, and we're going to focus on filtering TCP SYN packets. So in this case, I want to filter packets that only have the SYN flag set in a TCP packet. Now, this gets a little tricky because if you look at the TCP header, you'll see that the flags field comes about in TCP 13. So the 13th byte offset from 0, you see flags there. However, the flags field's interesting because it's not one value, right? It's not flags are on or off. It's actually multiple values, and it breaks down as such as what I've got on the screen here. So it's a single byte, but there are 8 individual bits, and each bit means a different thing. And you'll see in this case, the SYN bit is in the second position from the right, the position that has also a value of 2 if we're talking about the value of these individual bit positions when converted to decimal numbering. So if you don't remember our discussion earlier about converting hex to decimal, this next part might get a little tricky for you. So you might want to go review that or watch the next section here and then go back and look at that if it's a little tricky. This is definitely the part, kind of the last mile of BPF filtering that gets a little bit more advanced. It really trips some people up. So you really need to understand that hexadecimal conversion and understand the how to dissect packets and hex and bits and bytes and all that as well. So if you're not well versed on that, just bear with me here. See what you can pick up. Go watch that section again, and then come back so you can learn about bitwise filtering with BPFs. That's what we're leading up to and about to talk about. So as I mentioned, in this case, we're looking at flags, and we're only concerned about the packets with only the SYN flag set. In this case, the SYN value is in this 2 position. So one way you can filter this, and probably the easiest way, is to say TCP13 equals 2. And 2 there is a decimal value, right? And what we're saying is that if all the other flags within this field are set to 0 and only the SYN flag is set, so it has a value of 1, a 1 in the second position has a value of 2. So TCP13, that 13th byte, would just equal decimal 2. Now, similarly, if we were just concerned about, let's say, the reset bit, and everything else would be set to 0, and there was a 1 in the reset position, we would say TCP13 equals 4. Right? You see what we're doing here? We're concerned about specific values being set that result in that byte having one individual field. That works in this case scenario where we're only concerned about a single flag being set or only another set of flags being set, but it can get a little more complicated when we're looking for different combinations. We have to start masking out certain bit values. So that's what I want to spend the rest of our time here talking about BPFs discussing, is bit masking, which again gets a little complex, but bear with me. It's a useful thing to know, and I think as we go through different examples, you'll start to pick it up a little bit better. So let's talk about a different scenario related to the first. In the first one just a minute ago, we wanted to talk about any packet where only the SYN bit was set. So that was pretty easy because we could look for a single value of that TCP13 byte and just filter based on that single byte value. But what if we're concerned about any packet where the SYN bit is set, but not exclusively that, right? So it could be a SYN ACK, for instance, or something with SYN and a push set. Really, we're concerned about the SYN bit set, but we don't want to limit it to things where only the SYN bit is set. That gets a little bit trickier, and that's where we get into this concept of bit masking. And you can think of bit masking as bit level filtering. We've talked about byte level filtering already, so of course we have the precision where we can go into bit level filtering, and that's done with a technique called bit masking. I mentioned earlier that BPFs were to some degree infinitely flexible, and it's the ability to filter down at the byte and bit level relative to a specific protocol that makes that possible. Now, as an example here, the one we're talking about, again, is we just want to filter on anything where the SYN bit is set. I have TCP13 here on the screen, so you can see all the different positions. We know that the SYN bit is the second position, and it has a value of decimal 2. So how would we filter on that specific thing? What I want to do here is give you a framework for bit masking that you can use for any bit masking example. And this is relatively important, this process, so you may want to screenshot this or write this down or save this, because this is the technique you're going to use for any type of bit masking. Now, step number 1 is pretty familiar. It's what we've been doing thus far with byte masking, and that's to identify the protocol field location. So we have the protocol itself and the location of the field. In this case, we're talking about TCP13, right? We know TCP13 is where these flags are stored. Next, we want to create a mask that identifies the bits. So I want you to think of mask as basically something that tells the filter what bits within a byte to be concerned about. We definitely have to start with a single byte, but then once we have that byte, tell me what bits I'm concerned about. And we mask those, once again, by using binary, so ones or zeros. So in this case, we have 8 bits here, and I'm only concerned about the bit in the second position, the SYN bit. So what I would do is put a 1 in that field, so a 1 in the SYN location, and everything else would be a 0. And what's going to be read at that point from TCP dump or whatever's using your BPF is to say, only look at that specific value there. Only look at that second bit position. Now, if I was concerned about the first and second position, I would put 1s in both of those and 0s in the rest. You see what we're doing here? We're creating a mask. We're saying things with the 1 are things you're concerned about, right? So our mask is going to tell us what to look for. And once we know where to look, we specify the value we want to match. So we can say, okay, only look at this specific bit. And then once you're looking at that bit, match this value, right? So we're creating the mask, and then we're telling it what to look for within that mask. So it's a three-step process, and I want to show you what this filter looks like. And it's not as complicated as it may look once you realize what's going on here. So once again, we have TCP13. We're saying TCP13 is the byte we want to look at. From there, we have an ampersand. And this isn't a double ampersand. It's not a concatenation character or operator. It's a single ampersand. And that single ampersand tells the filter that what comes next is bit masking or bit level filtering. And we're finally left with really just two components. We're left with the bit mask, which is identified by OXO2, and the value we want to match, which is just decimal 2. So OXO2 is our mask. And again, that matches in hexadecimal this byte, but only with a single value set. So we've bit masked this to where the SYN bit is the only one we're concerned about. It's the only one with a 1, and that's equivalent to hex 02. It's also equivalent to decimal 02 in this case, so we could have just put 2, but I like to list the bit mask and hex because it makes more sense in the examples we're going to show later, show why that is. But in this case, the bit mask is OXO2, which says only care about the second position, and we want that to equal 2, decimal 2 in this case, because it is the second position. So this will give us any packet with the SYN bit set, not only the SYN bit set, but any packet with the SYN bit set. So it could, again, be a SYN-ACK or a SYN push or something like that, or some weird combination that isn't even to spec, like SYN reset or something of that nature. So what we're doing here is bit masking. Again, identify the protocol field location, create a mask that identifies the bits, specify the value you want to match, and then you're kind of there. So the syntax itself isn't too hard as long as you follow those 3 steps. So this may not make complete sense quite yet, but let's go through a couple other examples that will hopefully help you make better sense of bit masking. Now, I do want to show here as well that you can express these things in multiple ways. So this is how we just expressed it in our example, was TCP13 and OXO2 equals 2. So we're saying bit mask the second position and then look for a value of 2. We can also represent the value in hex as well. So of course, hex 02 and decimal 2 are the same thing. So this can be represented in a number of ways. And that's important to show you, because when you look for examples and look for references to other ways, other filters you might use, you'll see this, and just remember that this can be represented different ways. For me, I like to represent the mask generally in hexadecimal because I think that's the easiest way to do that. And I like to represent the value in decimal, so more like the top example. I'll flip-flop things around a couple times where it makes sense from a teaching perspective, but for the most part, I'll use the syntax at the top when we have to do any bit masking in this course. So now let's extend the previous example we just looked at a little bit. We just looked at how to look for and filter packets with the SYN bit set. So now we're going to look for those with both the SYN and push flags set. And again, we're not saying exclusively those 2 flags, but let's just say we're looking for things that just happen to have at least those 2 flags set. So it could be like a Christmas tree scan where all the flags are set, but we're going to search for that, again, just looking for SYN and push flags. So I'm going to put the TCP packet header back up here, and I'm also going to put the flags byte back up here so you can see the positions. And of course, we already know how to filter for the SYN bit, which is in the second position. It shouldn't come as a surprise that the push bit is going to be done in the exact same way, right? But instead of masking and filtering for the second position, we're going to mask and filter for the 4th position from the right, which is the one with the value of 8. So we're going to take that and create a second primitive and just concatenate those together with an AND operator. And that filter is going to look like this. So on the left, we see the filter we'd already created, TCP13 and OXO2 equals 2. That's saying to mask off the second bit and look for a value of 2 within it. Then we're going to concatenate with the AND operator, 2 ampersands, and say TCP13 and OXO8 equals 8. So in this case, we're masking off the 4th position, which is OXO8, and then we're telling it to look for a value of 8 in this particular field, and that's going to give us, this filter will give us any packet that has both the SYN and push flags set. Not something you're going to see a lot, but maybe that's why you're looking for it. Maybe you're looking for a certain type of anomaly, a specific type of scan, something of that nature, and this is the filter that will help you do that. The next filter I want you to be able to create is how to look for TCP packets with only a specific couple of flags set. And we did that earlier by looking at packets with only the SYN flag set. But what if we want to look at packets with the SYN and ACK flags set? And I want you to specifically do this using bit masking. It can be done another way, but I want you to try this using bit masking. So feel free to pause this and go ahead and try it yourself. But otherwise, I'm going to go ahead and go through the example here. So I'm going to go ahead and put up the TCP header once again, along with the flags byte, so you can see what areas we're interested in. In this case, we're interested in the SYN bit, which is in the second position, and we're interested in the ACK bit, which is in the fifth position, or if you're going to divide these into nibbles, it's in the first position of the higher order nibble. So that's going to be important because that's exactly what we're going to do. I'm going to go ahead and put the answer up here so we can actually work through what's going on. In this case, once again, you see we're looking at TCP 13, and then we're going to mask off the bits we're concerned about. And we're masking off OX12. And it's important I say OX12 because it's not 12, it's 12. And the reason, remember, this is hexadecimal representation. The first value represents the higher order nibble, and the second value represents the lower order nibble. So if we look at the second value, the lower order nibble, we see we're looking at 2, and 2 represents position 2 because there's a 1 in that bit. So the rest of the bits are zeroed out in that nibble, and that one's enabled, which gives us a value of 2. Now, if we look at the left number, so in OX12, if we're looking at the 1, that's representative of the higher order nibble. And in this case, when we're looking at the higher order nibble, those values aren't actually 16, 32, 64, and 128. They're still 1, 2, 4, and 8. And in this case, ACK would be in the first position. So when that bit is set and none of the rest of them are set, that gives us a value of 1. So ultimately that gives us a value of OX12, which basically says look at the second bit in the lower order nibble and look at the first bit in the higher order nibble, or said another way, look at the second bit in the byte and the fifth bit in the byte. Those are the things we're masking off, and that's what we're concerned about. And for those things to be enabled, we're looking at a value of decimal 18, or written another way, a value of OX12. So that's just two ways of representing the same thing, and that can be a little tricky, especially if you're looking at examples elsewhere and they're written both ways. But I do want to show you, again, these things can be represented in hexadecimal or in decimal, and in this case, OX12 is equivalent to decimal 18 in this case. Again, this is a matter of looking at things from the perspective of nibbles and hexadecimal versus the entire byte and decimal. So hopefully this is starting to make a little bit of sense to you now. If not, really, I recommend going back and reviewing a little bit about how hex and decimal translate back and forth when we're talking about mapping out bytes, because that's really the key to understanding what we're doing here. I'm going to go through just one more example of bit masking, and I want to divert a little bit away from the previous example where we're focused on the TCP header and actually pivot over to the IP header to show you an example of this being done in another scenario. Generally, an IP header is going to be 20 bytes. That's what you're going to see most often, but it can be larger based upon a certain number of configurable options. So in this case, what we're going to do is look for IP headers whose size is greater than 20, so greater than 20 bytes, that is. So if you look at the IPv4 header here, you see that the header length field is in the very first byte. So it's in byte 0, but it's only in half of that byte. So it's encompassed in the lower order nibble. The entire lower order nibble contains all the bytes we're concerned about here. Now, keep in mind, too, this is also a calculated field. So whatever the value of this field is, you multiply it times 4 to get the TCP header size. So when we say we're looking for an IP header size greater than 20 bytes, we're actually looking for an IP header length value greater than 5, because 5 times 4 is 20, and that's what we're looking at here. So we'll talk about that more when we talk about IP version 4 later, but just know that it's a calculated field, and ultimately we're looking for any value in this field greater than 5. Now, our filter in this case, you can go ahead and try to work it out yourself. If you want to, go ahead and pause the video now. But we're going to go ahead and show this. I'm going to show you how we came up with it. In this case, our filter is IP0 and OXOF greater than 5. So remember, we're using the IPv4 protocol here, so that's IP. We're starting at byte 0, so it's IP0. Now, in this byte, we're only concerned about the lower order nibble, so the lower order bits, so the rightmost 4 bits. We're not concerned at all about the leftmost bits. So to do this, we're going to mask it out appropriately. OX0F. What we're saying here is all of the bit values in the higher order nibble are set to 0. So that's 4 zeros, and that equals, of course, hex 0. So we're saying we don't care about any of that. We only care about the lower order nibble. So in this case, all those values are set to 1. And with all those set to 1, what we're saying is add 1 plus 2 plus 4 plus 8. And that gives us 15, which is equivalent to hex F. F is 15, and F is the hexadecimal representation of 15 decimal, right? So we add those together, convert that to hex, and we get F. So what we're saying here with OX0F is we only care about the value of the lower order nibble in these bytes. So another example here, again, we're focused on multiple bits, but again, we're focused on bits and not necessarily bytes. So once we mask that out appropriately, pretty straightforward. We're looking for things greater than a value of 5, so we just put greater than 5. Again, it's a multiplied value, so 5 times 4 is 20. We're multiplying that value times 4, and that gives us 20 bytes. So anything greater than 5 means we have greater than 20 bytes in this packet, and that's in this case of interest to us because we're looking for specific size IP headers. So bit masking, again, very, very effective. It's a little tricky to figure out, especially if you're a little hazy on hexadecimal conversion and dissecting packets at that level, but it's another reason why you need to get proficient in that specific area. That's going to bring us to an end on this lesson all about Berkeley packet filters. Now, we started by looking at BPF syntax, and the great thing about BPFs is the syntax is fairly straightforward. It's not really hard or challenging to grasp from a syntactic level. Nothing like learning a new programming language, and that's a great thing because with that in mind, we were able to look at a ton of common expressions really focused on ports, protocols, and hosts that are going to get you 90% of the way there or more in most cases. For some of you, it might get you 99% of the way there. You may never need to go deeper. And I know most of the time when I'm doing filtering with BPFs, I'm generally limiting it to, again, host, protocols, or ports. So that's great that that's very easy and it's universally accepted amongst a lot of tools. However, if you want to get a little more focused, you have to get into both byte level filtering and bit masking. And those, especially when you get to bit masking, can be quite a bit of a challenge, especially if you're not fully comfortable dissecting packets in hex and doing hexadecimal conversions and all that. So again, you want to go back, and if you want to really master bit masking, you need to make sure you master all those other techniques I talked about in an earlier lesson with decimal and hex conversion. And really, you're not really going to understand it or fully grasp it well until you do a lot of it. So what I'm going to do here is challenge you to go and look at the various protocol headers and look at the protocol maps we provided you and just start picking individual bits or groups of bits in specific fields. Look at those and start writing filters for them. And you can do this on your own network. And in a later section of lesson of this section, I'm going to show you how to apply those in TCP dump and Tshark and Wireshark. So not just create them, but applying them as part of this as well. But I'm going to show you how to do that. And I want you to start applying those on your network and seeing what you can find. Just start taking a specific numerical value and looking for things greater or lower than that. Or write filters that match the specific thing. Maybe you can write a bitwise filter or bit-masked filter that will match IPv4, and that way you can negate that and say, show me anything that is not IPv4. And in that case, you can look for IPv6 traffic on your network. You might not think there is any, but unless you specifically disabled it on Windows or Linux, then you probably have some IPv6 traffic floating around. So that's a good exercise. So if you really want to learn the intricacies of BPFs and get into bit masking or bitwise operation, as it's called sometimes, you really need to practice it. I'm going to give you opportunity to practice that with some of the additional materials in the course, but you kind of need to be your own self-starter and dig into that more. I'll also provide some example links that provide all sorts of additional examples of bitwise and byte level filtering. So you can dig through those, see some of the common ones, and maybe tweak them or start playing around with those on your own. That's really how you're going to get better at this. But again, Berkeley packet filters, incredibly useful, one of the more accepted and common ways to filter packets, and really another method that's going to allow you to make sense of the trillion truths you have to deal with in packet analysis and get down to the things that are really going to answer the questions that you're asking.